In this video, we're going to differentiate functions involving the chain rule. The chain rule is all about finding derivatives of composite functions. So it's often written like this to begin with. And the idea is that we first take the derivative of the outer function, in this case f prime, and leave the inner function alone, and then multiply by the derivative of the inner function, in this case g prime of x. Another way this is often written is we're taking the derivative with respect to x of some function where the inner function u is a function of x, and we take the derivative of the outer function with respect to u, and then we multiply, which again, u is the inner function, and then we multiply that by the derivative of u with respect to x. Now, we have a lot of differentiation rules already, and we can now rewrite all of them incorporating the chain rule. For example, taking the derivative with respect to x of some function of x u to the n power, we would multiply the n down, subtract 1 from the exponent, and then multiply by the derivative of the inner function. Similarly, the derivative with respect to x of e to the u is going to equal e to the u times the derivative of u. And we can do this also with all the derivatives of our trig functions. We also have the derivative of an exponential where the base is not e, so base b in this case, and that equals b to the u ln of b times u prime. And there may be some others here that I'm forgetting, but we'll just come back and fill them in as we need them. So let's jump into problems. With these first few, if you already have some experience with the chain rule, you might find that they're not too difficult. You can go ahead and pause the video, try them on your own, and then check your answers. But jumping into A, we've got an inner function of 3x squared plus 4. I'll go ahead and highlight that in yellow. There's our inner function. H prime of x is going to equal bringing the 2 down using the power rule, leaving the inner function alone, and then raising it to the first power, right? Subtracting 1 from the exponent. Then we multiply by the derivative of the inner function, which in this case is going to be 6x, and we can rewrite that as 12x, 3x squared plus 4. Moving on. Same idea here. We probably want to rewrite this as 4x squared plus 5x minus 1 to the 1/2 power. Y prime, we're going to bring the 1/2 down using the power rule, leave the inner function alone, subtract 1 from the exponent, and then multiply by the derivative of the inner function. Here the inner function is 4x squared plus 5x minus 1, and we get 8x plus 5. We're going to go ahead and rewrite this so we have no negative exponents. So we're going to put the 8x plus 5 in the numerator. The 2 from the half goes in the denominator. And then we have 4x squared plus 5x minus 1 to the 1/2 power. And you can write a square root down there at the bottom if you'd like. Either way is fine. Moving on. Now we've got a trig function. Now we have to remember what that little square means. It means first we figure out the tangent if we were evaluating this, and then square the result, right? So squaring is really the outer function here. So f prime of x, we're going to take the derivative of the squaring function, if you will, the outer function, leaving the inner function alone to the first power. But then we're going to multiply it times the derivative of the inner function, which is going to be secant squared x. Like that. Part G. Here, again, we have a composite function. The inner function is x squared, though. So first we're going to take the derivative of the outer function, the cosecant. Of course, we have a constant multiple with this 5. I'm just going to put that on the outside real quick. And we'll multiply that by the derivative of cosecant is negative cosecant cotangent. So there's the derivative of the outer function. And I have to multiply that by the derivative of the inner function, which is 2x. So we're left with g prime of x equals negative 10x cosecant x squared cotangent x squared. All right, moving on. Okay, so here we have an inner function of cotangent, outer function of sine. Y prime, the derivative of sine is going to be cosine, leave the inner function alone. And then we multiply by the derivative of the inner function, which is negative cosecant squared x. There's not really a really nice way of writing this one. I'm just going to go ahead and put the negative cosecant squared x in front, and that's multiplying the cosine of the cotangent of x, like that. Part E. Okay, so now we have an exponential. So real quick, in blue off to the side there, right? Where is it? There it is. Right here, the inner function is what we're raising the exponential to, right? That's that function up in the exponent. And in this case, we have a cosine 2x in the exponent right there. So when we go to take the derivative of the first part, we know the derivative of e to the something is going to be e to the same thing. But then we have to multiply by the derivative of the inner function, which is the cosine of 2x. And hopefully you're looking at this saying, hey, that's going to be another chain rule because we have the cosine function, but we also have the 2x function. So we'll get to that in a second. Over here, on this side, we're taking the derivative of cosine first, which we know that to be negative sine. So I'll write a minus sign like that. And we leave the inner function alone, but then we have to multiply by the derivative of the inner function. So hopefully you're okay with me doing two things at once, right? I've got, let's see, this part here in blue is all of this, which is not done yet because I still have to take the derivative of the inner function. And this part here in green is, well, with the minus sign, all of this, right? And again, I have to still take the derivative of the inner function and back there. Okay, so continuing on, we're going to have e to the cosine of 2x, and then the derivative of cosine, of course, is negative sine of 2x, but then we have to multiply by the derivative of the inner function here, which is going to be 2. And that takes care of the blue part. And then what do we have? We've got minus sine e to the 2x, and then the derivative in back of e to the 2x is going to be e to the 2x times the derivative of the inner function, which is the 2x right up there, and we're going to get 2. So maybe rewriting this like this, we have a negative 2 sine 2x e to the cosine 2x minus 2 e to the 2x sine of e to the 2x. I guess we could factor out a 2, but let's just go ahead and leave it there for now. All right, moving on. The first thing you're noticing is that we have a quotient, right? And so if we rewrite this as x to the third over 5x squared minus 4 to the half power, we have a numerator, we have a denominator, we're going to use the quotient rule. We could rewrite it if we wanted to as a product involving a negative exponent with that half, and then use the product rule, but let's just go ahead and do quotient rule for now. So we have q prime of x. We have the bottom function times the derivative of the top minus the top times the derivative with respect to x of the bottom. So I'm choosing to wait to take that derivative. I could do it right now, but I'm not. All over the bottom squared, like that. Since we're squaring the half power, it's to the first power. So now, with this guy right here, when we take this derivative, we have to use the chain rule, right? We're going to use the power rule with the half exponent coming down in front and then subtracting 1 from the exponent. And then we're going to need to multiply that by the derivative of the inner function. So to that end, we have what? We have 3x squared times 5x squared minus 4 to the half power minus x to the third times 1/2 5x squared minus 4 to the negative 1/2. And then derivative of the inner function is going to be 10x. And then on the bottom, we have 5x squared minus 4. All right, so we have this negative exponent here. And right there. And we also have a compound fraction. So we can treat this in a couple different ways. This time, let's just go ahead and make two fractions in the numerator, and then we'll combine them by making a common denominator. So let's see. So far, we have 3x squared times 5x squared minus 4 to the half power. And then in back, you'll notice we have a half here, and we have a 10 there, so those will give us a 5, and we have x to the fourth, right? We have x to the third there, and we have another x there. So that's going to give us 5, so let's write minus 5x to the fourth, and then we've got this 5x squared minus 4 to the half power. So I think that numerator is all taken care of. And then, of course, in the denominator, we've got 5x squared minus 4. And so this guy has a 1 underneath. We want to make a common denominator. So we're going to go ahead and multiply top and bottom of the first fraction by 5x squared minus 4 to the half power, like that. And then we'll have a common denominator in the numerator. So moving on, we're going to have, when we multiply these guys here, this guy and this guy, we're just going to add the exponents, right? So we're going to get 3x squared times 5x minus 4 to the first power. And from that, we're going to subtract 5x to the fourth. And then on the bottom, we're going to have 5x squared minus 4 to the half power. Now this is being divided by 5x squared minus 4, like that, over 1, which is the same as multiplying by the reciprocal. So we can rewrite that as multiplying by 1 over 5x squared minus 4. And from there, if we go ahead and distribute here, we're going to have 15x to the fourth minus 12x squared minus 5x to the fourth. And on the bottom, we're going to have 5x minus 4, 5 squared x minus 4, I should say, to the, I've got to add the exponents, right? Way over here, we have a 2 over 2 exponent. So we're going to add those, and we're going to get 3 over 2. And then we can combine the first and last terms, and we get 10x to the fourth minus 12x squared over 5x squared minus 4 to the 3/2 power. At this point, you could, if you wanted to, factor out a 2, factor out an x squared on top. It doesn't cancel with anything on the bottom, so I'm just going to leave it there for now. So with this one, first notice that we have a product of two functions. So we're going to be using the product rule. Let's rewrite it with a fractional exponent. So we have 4x squared minus 3 to the 1/3 power. And then applying the product rule, we're going to have the first function times the derivative of the second function plus the second function times the derivative of the first. And so I haven't taken any derivatives yet. That's just been a matter of using the product rule. And hopefully we're noticing right here we're going to have a chain rule, and we're also going to have a chain rule over here, right? Because we know the derivative of e to the x is itself, but then we have an inner function, which is that negative x. So we're going to have to take the derivative of negative x and back there. So going ahead and doing that, we're going to get what, the 1/3 in front, 4x squared minus 3, to the subtract 1 from the 1/3, we're going to get a negative 2/3, and then we multiply by the derivative of the inner function, which is going to be 8x, plus 4x squared minus 3 to the 1/3, and as I just mentioned, we're going to take the derivative of e to the something, it stays the same, but then we have to take the derivative of that inner function, which is going to be -1. So cleaning this up so we don't have any negative exponents, we're going to have, in this first term here, I think the only thing that stays in the numerator is the 8x. So we have 8x over, we have a 3 in the bottom, we have e to the x in the bottom, and we have this 4x squared minus 3 to the 2/3 power. Plus, actually let's make it a minus because of that -1 there. On top here, we're going to have a 4x squared minus 3 to the 1/3 power, and then we have the e to the x going to the bottom there. Making a common denominator, let's multiply here by 3 and 3. And also we're going to have to multiply by 4x squared minus 3 to the 2/3 power. Like that. Okay. Here we have our 8x still. The denominator stays the same. On top here we have a 3. When we multiply these guys in yellow, we've got to add the exponents. And that comes out very nicely because 1/3 plus 2/3 is just 1. And so we just end up with a 4x squared minus 3 in the numerator. And we still have the same denominator. So we have our 8x. Distributing that 3, we're going to have negative 12x squared plus 9. And in the bottom, we're going to have 3e to the x, 4x squared minus 3 to the 2/3. And maybe rewriting it this way. And we're pretty much there. Moving on. All right, so with this one, we've got a couple things going on here. We've got an exponential with a base other than e here, which we'll talk about in a moment. And then here we have a whole bunch of chain rule going on. So let's go ahead and take a look at the first part. We know that the derivative with respect to x of e to the x is e to the x. And as we mentioned at the beginning of the video, we also have this where b is some other base, and it looks something like that. Now, if we replace these x's with some function of x, u, like that, we have to multiply by u prime, right? That's the chain rule embedded in this guy. And so that's what we have here with this x squared. So our base is 7, so the derivative of 7 to the x squared will be 7 to the x squared times the ln of 7. Okay, that's this part right here. But then we have to multiply that by the derivative of the inner function, which is going to be 2x. So that takes care of that piece. Now, over here, we have a secant function that's being raised to the 4th power. So really, the 4th power is the outer function. If I were to come up here real quick, this 4th power, which I'm erasing right now, is really taking that whole thing to the 4th power like that. Okay, but I'm going to go back to the original notation because it's the correct notation. So we've got that 4th power on the outside. We first need to use the power rule. So the 4th power comes down. We're taking the secant to the 3rd power now, and we're leaving everything on the inside alone. Okay, so the outer function was raising to the 4th power. Now we have to take the derivative with respect to x of the next inner function, if you will, or the next level inward after the 4th power, which is going to be the secant function. Like that. Okay, so continuing on, I'm going to go ahead and take this and put it in front like 2 ln of 7, so all that is constant, x times 7 to the x squared minus 4 secant cubed sine of 3x. And then we need to take the derivative of secant, which is secant tangent. So we have secant of sine 3x times the tangent of sine 3x. And then we have to multiply by the derivative of the inner function, which now, that's this guy in green. A lot of links in this chain rule, right? And so now all we have left is to take that last derivative and back. Again, it's going to require chain rule because you have the sine function and you have that 3x function, and multiply it times everything else here, and we should be in good shape. So the derivative of sine is cosine. We leave the 3x alone, and finally we multiply that by 3. Now instead of rewriting this all over again, I'm just going to take this 3, I'm going to multiply it times that 4, and so we're going to have a 12 out in front of that term. And that's about as pretty as it's going to get, right? So a lot of steps in that chain rule, right? We've got to, every time we come across a function involving composition, we've got to know which is the outer function, which is the inner function, which is the inner function, if you will, and then keep going like that. Okay, so with part J, we have g of x equals 4 to the third, which is raised to the second, which is raised to the x power. So this is an exponential with an inner function. In other words, we are taking the derivative with respect to x of some base, in this case 4 to start off with, and that's raised to the u power in purple there. And the derivative of this is going to be b to the u times the ln of b, right? And then we have to multiply that by the derivative of the inner function, which is u prime. So this is what we're doing with this problem, and we're going to have to do it multiple times because you have, well, let's just get started and you'll see. But if we go to get g prime of x, the first thing we're going to do is we're going to write b to the u power. So we have our b base is 4, and we're going to raise that to the u power, which is 3 to the second to the x. Next thing we need is ln b, so we write the ln of 4 like this, and then we need to multiply by u prime, which is going to be, I'll do it in purple here, the derivative with respect to x of the inner function, which is 3 to the second to the x power, like that. And so there's our first step. You can pause it and kind of double check everything, but again, we have this part here, we have this part here, and then we have in light purple that part there. And now we have to take a derivative again of this bit in back, which I'm going to take that now and I'm going to change it to black. Okay, so continuing on, we're going to copy the 4 to the third to the second to the x ln of 4. And now we get to do the same thing with this function, but the purple part now is the exponent here, right? So we are going to take, multiplying by first the base to the u power, like that. Again, ln of the base, which in this case is 3, and then we have to multiply it by the derivative with respect to x of the inner function, which is 2 to the x. And so we're closer, but we're still not quite done yet. We still have a little bit more to do here. I'll put that way down there. We still have to do the part in back, right? So this part right here, we have to still deal with. So we'll make that black. So we've got 4 to the third to the second to the x ln of 4 times 3 to the second to the x ln of 3. And then finally, we've got the base raised to the x power times the ln of the base. So I've done this part and this part. And then the inner function, well, it's just x. And the derivative of x, if you were to try to apply the chain rule to get that u prime, is just going to be times 1, which of course does nothing, so we can leave it off. And there we go. So we just applied this rule 3 times. Okay, let's go on. Example 2, they give us g of x is equal to the square root of 4 plus 3 f of x, where f of 2 is 7, f prime of 2 is 4, then find g prime of 2. So the first thing we're going to do is we're going to find g prime of x. So to that end, maybe we should rewrite this with a fractional exponent first. So I've got g of x is equal to 4 plus 3 f of x to the 1/2 power. And so g prime of x, we're going to use the power rule first, right? That's the guy on the outside there, the power rule. So we're going to bring the 1/2 down in front. We have 4 plus 3 f of x to the negative 1/2 power, but then we have to multiply that by the derivative of the inner function. Well, the derivative of 4 is 0, it's constant. The derivative of this piece, well, we've got 3 as a constant multiple, and then we have f prime of x. And so we'll go ahead and rewrite this so we don't have any negative exponents or compound fractions. So we're going to have 3 f prime of x in the numerator, and in the bottom, we're going to have 2 f plus 3 f of x to the 1/2 power. And you could use a square root down there if you want. Either way, if that makes you happy. Okay. Now we're going to go find g prime of 2. So now we plug in 2 for every single x, like this. So we have 2 on the bottom, 4 plus 3 f of 2 to the 1/2 power. Well, f prime of 2, I'll highlight it in purple here, is 4. So we're going to have 3 times 4 in the numerator. And then in green, we have f of 2 is 7, right? So we're going to get 2 square root of 4 plus 3 times 7. Well, that's 12 on top, or, well, yeah, I was going to cancel with the 2 down there. So that's a 12 on top, but it cancels with the 2, so let's just put a 6 on top. And then we have the square root of 4 plus 21, which is 6 over the square root of 25, which will give us 6 over 5. All right, moving on. They want us to find the equation of the tangent line to this curve at x equals 0. So we've played this game quite a bit. We need a point and we need a slope, and then we can plug it into y minus y1 is equal to m times x minus x1. So we can plug in a 3 in for x1. We need a y value, right? So the way we're going to do that is we're going to take our function, y equals 2 tan of, what's that going to be, 3 pi over 4, like that. Tangent of 3 pi over 4 is negative 1, so we have negative 2. So we have the point 3 comma negative 2 as our point of tangency. All right, so we've got y minus negative 2 equals, I don't know my slope yet, I'm just going to put a big question mark there for the time being, x minus 3. Okay, now we're going to need to go ahead and take a derivative and come up with, to help us come up with the slope of the tangent line. So y prime is going to equal 2, derivative of tangent is going to be secant squared. In this case, we have pi over 4x still inside. And then we have to multiply that by the derivative of the inner function, which is just going to be pi over 4. So I'm going to bring the pi over 4 in front, multiply it by the 2, right? I'm talking about taking this and this, multiplying those together, I get pi over 2 in front, secant squared of pi over 4x. So there's our derivative. Let's do this. At x equals 3, y prime is going to equal pi over 2 secant squared of 3 pi over 4. Now, we need to be able to evaluate the secant of 3 pi over 4. Maybe you remember the cosine of 3 pi over 4. 3 pi over 4 is in quadrant 2. Right, we're talking about here. And the cosine is going to be negative root 2 over 2. That is 3 pi over 4. Another way to write negative root 2 over 2, if I unrationalize it, meaning if I multiply the top and bottom by root 2, so I'm going to get negative 2 on top, 2 root 2. It becomes negative 1 over root 2. And so if that's the cosine, the secant is going to be the reciprocal of that, meaning the secant of 3 pi over 4 is equal to negative root 2. Okay, so if that's the case, I can rewrite this as pi over 2 times negative root 2, and that's being squared. Well, of course, that gives us pi over 2 times 2, which will just be pi. So that's the slope of our tangent line. We get to put that where the question mark is. And now we're in pretty good shape. We can distribute. We get pi x minus 3 pi. We subtract over the 2. Pi x minus 3 pi minus 2, and we have it. All right. Example 4. We want to find a function f of x such that f prime of x equals x cubed secant squared x to the 4th minus x e to the x squared. And we're going to do this by trial and error. Later on in the class, we'll come up with more systematic ways of getting f from f prime in a situation like this. But take a moment and just look at it and see what you recognize. Hopefully by now we have all of our trig derivatives memorized and our exponential derivative memorized. So I'm hoping you're looking at this and thinking, oh, secant squared, that makes me think of something. What do I have to take the derivative of in order to get secant squared? And I'm hoping everybody's thinking tangent. So if we start with just f of x equaling tan x, okay? This is not correct, but it's a start because you know the derivative in this case would be secant squared x, okay? But we're dealing with chain rule in this whole video, right? So notice we have an inner function here. We probably need an inner function in there too. So let's see what happens if we put x to the 4th in there. So if we put that x to the 4th in like this, let's go ahead and take a derivative of what we have here using the chain rule. The derivative of tangent is secant squared, leaving the inside alone, times the derivative of the inside, right? Isn't that the derivative of the inside? I think it is. And now if we go ahead and compare, we have this, which is fantastic. That gives me that whole piece. But look what else we have. We have this x to the 3rd, which is right there. But what do we have in our derivative that we don't want? That 4. So how are we going to balance out that 4? Well, it sure would be nice if we had a 1/4 in front, so it could multiply that 4. A 1/4 in front. Okay? So if you don't see it already, pause the video and take a derivative of this using the constant multiple rule, followed by the derivative of tangent with this, which is secant squared, leaving x to the 4th alone, and then multiplying by the derivative of the inner function, chain rule. And I think you're going to find that it gives us this whole first bit here. Okay, and so that's great. We made some good progress. Okay, let me go ahead and write that properly. So again, we've got secant squared x to the 4th. The derivative of the inner function was 4x to the 3rd, but that 4 is going to multiply the 1/4, and I'm just going to be left with x to the 3rd. So we're in really good shape for this first part. Now we've got to deal with back somehow. Well, I'm hoping you're noticing right off the bat that you need an e to the something, right? So if I put minus e to the x, if I took that derivative, I'd get minus e to the x, which is not exactly what we want. What we want up there is an e to the x squared, right? And so if we went ahead and took this derivative what would we get? We would get e to the x squared times the derivative of the inner function, which is x squared. We get 2x. And again, comparing this with what we're trying to get, look at that green x there. We have it right there. And we already have the light blue e to the x squared. So the only thing we don't want is the 2, kind of like the 4 in the previous part. So if we had a half here, they would cancel off. So I'm going to put a half up there. And so now, if we come back here, I just erased it, but if we write the half, derivative of e to the something is e to the same thing, times the derivative of the inner function gives us this. And then we get this really nice cancellation with these guys. And guess what? We're there. So we reverse engineered this. This is our function. And as we discussed before, we can always add a constant of any kind. So I'm just going to put plus c to represent the collection of all possible constants. Because when you take the derivative of a constant, of course, it's 0. And imagine a plus 0 and back there. So there it is. We did it. All right. Last one. Couple parts to it. They want us to look at this function x squared minus 9. And they want us to graph f of x and list all the values for which x is not differentiable. So this might not be real clear yet how this is going to go as far as, well, how do I know it's not differentiable? Well, let's just start graphing and seeing what happens. So we'll just go ahead and sketch this. So I want to start off graphing a different function. I want to graph the function g of x. I'm just going to write it above. G of x is equal to x squared minus 9, because we know what that looks like really well. So we're going to have a y-intercept of -9 way down there, and x-intercepts at -3 and +3. And when we go to graph this, right, you can actually plug in the values. I think you're going to find all those 3 points are on this parabola. You can think of it as a parabola that's been shifted down 9 units and is opening up. Not the best picture in the world, but good enough for our purposes. So there's the function g of x. Okay. Now let's think about f of x, and I think I'm going to do f of x in some contrasting color like green. So we're going to do f of x here in green. Now, if you think about it, we never have negative y values, right? Because we have the absolute value. If you plugged in 4 up here into the blue function, g of 4, right? G of 4, you're going to get 16 minus 9, which is equal to 7, which is clearly positive. If we do f of 4, you're going to have the absolute value of 16 minus 9, which, hey, guess what, is also 7. So at 4, they have the same y value. As a matter of fact, they also have the same y value at 5 and 6 and 7. They have the same y value anywhere along here where g is already positive. F is going to be exactly the same. Okay, and you can pause the video and try values. As a matter of fact, if you plug in 3, f of 3 is going to be 0 also. So this point is also on our curve. And it kind of makes sense. Basically what it's saying is when these y values are positive, hey, guess what? It's positive inside here, so the absolute values aren't really doing anything, right? We just get the same positive result. And the same thing's going to happen. I'll let you check it out on your own, but the same thing's going to happen over here in the negative side. Okay, so that's a good start, but what's happening in the middle? Well, let's take the easiest value here. Let's take 0. What's g of 0? Well, it's on the graph. It's going to be 0 squared minus 9, which is -9. What happens if I do f of 0? Well, that's going to be the absolute value of 0 squared minus 9, which is going to be the absolute value of -9, which is not the same as blue. In other words, I have a point on green way the heck up here at +9. So that point down there ended up here. Pause for a moment and think about that. it kind of makes sense. We can't have any negative y values on f because we have absolute values. So it seems reasonable that that negative 9 just got flipped up. But using that same logic, and feel free to plug in points. I'm not going to plug any more points in, but if you imagine this point here should go up there, and this point here should go up here. And if we did this for all the blue points down below the x-axis, we're going to get a curve like that. And so green now is your function f of x equals absolute x squared minus 9. And so you can do this with just about any function that you already know the graph of that's inside your absolute values. You're just going to take the negative parts, so to speak, the negative y values, and you're going to reflect those points so they have positive y values. So we've gone ahead and sketched the graph. So now we want to find all values of x for which f of x is not differentiable. Well, if we start thinking about tangent lines, there's two places where we have sharp turns. We have, and everywhere else seems fine, right? There's no holes, there's no gaps, right? It's continuous along its entire domain. And there are no vertical tangents. So the two places, we'll just go ahead and write this up here. We'll say f is not differentiable at x equals negative 3 and x equals 3 because we have sharp terms there. All right, moving on. Next, they want us to find f prime of x and sketch its graph. All right, well, let's go ahead and find the derivative first. So they're giving us a hint here that we can rewrite anything in an absolute value as the square root of that thing squared. So let's see if we can get that done. If we think about f of x equaling absolute x squared minus 9, we can rewrite that using the hint as the square root of x squared minus 9 quantity squared. And we can further write that up this way to allow us to take a derivative easier, like this. Now, as tempting as it is to let the square and the half power multiply and just undo each other, that's not going to work on the entire domain of this function, right? Because we are only dealing with positive results, right? And if you were to undo this squaring with that square root, then you're introducing all the negative results. So just something to think about. But let's go ahead and find a derivative. We know how to use chain rule. That's what this is. You have a function within a function within a function. The outermost function, here, let's highlight. Outermost function is in green, the square root function. The middle function is in blue, that's the squaring function. And then the innermost function is in purple. So if we start by taking the derivative of the outermost function, we're going to put a half in front, leave everything on the inside alone, and subtract 1 from the exponent. And on the inside, we have this, x squared minus 9, like that. Then we have to multiply by the derivative of the inner function, right? So now we're going to take the derivative of blue, right? We've got to take the 2 down in front. And we've got x squared minus 9. I probably should have done that in purple, huh? To the first power. I'm not going to write the first power. And then we have to multiply again by the derivative of the inner function, right? This guy inside here, which is just going to give us 2x. And so cleaning this up, what the heck do we have here? Well, the half and one of the 2's cancel, so that's kind of nice. We're going to go ahead and rewrite this as, let's write 2x times x squared minus 9 in the numerator. And in the denominator, we have x squared minus 9 squared to the half power, which is the same as having all that in a square root. And they want us to write the final result using absolute values. So if I come back down here to the bottom for a moment, and rewrite it like that. And then going back to the highlighted yellow hint, we've got 2x times x squared minus 9 over absolute x squared minus 9. They wanted the final result written in terms of absolute values. So there we go. We found the derivative like that. Now, the last thing they want us to do is sketch the derivative. So I'll do my best to make this look good, and if it looks horrible, maybe we'll graph it on the computer to see what it looks like. But let's get a y-axis and an x-axis, and we'll get going with it. Okay, so once again, I'll just put a 3 here and a -3 here. And I'm going to sketch the green graph, which was our original function. I may kind of mess with the scale a little bit to make it look a little bit better. At least I'll try. Okay, and this is just a sketch. This is by no means accurate. It already looks really wonky to me. Let me see if I can make it look a little bit better. All right, that's going to have to be good enough. So there's f of x. Now, if we start thinking about the graph of the derivative, I'm not going to try to graph this because I know what it looks like, because guess what? I don't know what it looks like. And the one thing I guess we can make an argument for is it has linear, a linear, what's the word I'm looking for, characteristic to it, I guess, because you can imagine the x squared terms, or factors I should say, kind of canceling, and you're left with just a linear. And it makes sense if you think about the horizontal tangent line, say right there, and that means we're going to have our derivative is going to go through the origin like this, right? And if we think about, here, let's use the ruler, over here, right? Imagine right there, we have tangent lines that are positive, correct? And they're getting a little less positive, and they're getting a little less positive. And so on this side, we have maybe tangent lines that are looking, and this is not going to be accurate, but maybe looking like that. And then we get tangent lines on this other side that are negative, right? Negative, right? So that means that my orange derivative function is going to go below the x-axis. And so here, let me see if I can line this up again. So we have that. Okay, and the derivative doesn't exist at +3 or -3 because we have a sharp turn, so I'm going to put a hole there and a hole there. Now, you might be thinking, well, how does he know that it's linear? Well, I know it's linear because guess what? This part right here is parabolic, right? It's an x squared. It's really, again, it's not drawn to scale, but it's really -x squared plus 9. And if you took that derivative, you would get -2x, and so that is a linear derivative. Over here, on the other hand, right, over here, we have a whole bunch of negative slopes of tangent lines, right? And on that section, if you remember, it's the same as the g of x in blue, right, up there towards the top. So so there we're going to get negative, right? Negative slopes. So we're going to have a negative linear function, but it starts super negative and gets less negative, less negative, less negative. And so we're going to end up with something a little bit like this. And again, the idea being that, that if you imagine a slope of the tangent line way the heck over here, as opposed to a slope of a tangent line way over here, they're both negative, but the first one is way more negative than the other, right? So we're steeper the further we get away from the origin, but they're both negative. So that's why we're going down towards negative infinity there on the orange function. On the other hand, over here, we've got positive slopes of tangent lines, and they're getting steeper and steeper and steeper the further away we get from 3 to the right along the x-axis. So here, we're going to have something that kind of looks like this. And we're going to get a linear like this. And these really should line up properly. Not my best work, but I'm going to leave it for now because this is just a sketch, and we'll look at a computer-generated version of this. So there it is. That's going to be our f prime of x, and we've got it. So I kind of like that last problem because it's kind of an interesting application of the chain rule in order to get a derivative of a function involving absolute values that maybe you haven't tried before. So when you go down to the problems you're going to do on your own, you're going to see something similar to this, and you can kind of follow the same steps as what we did here. That pretty much covers it. So you're good to go to go ahead and do these problems.